one more application of refraction that we're going to talk about today. And this one we're going to talk about today and tomorrow and probably the next day as well. We're talking specifically about curved lenses. Lenses are optical devices that bend light in a predictable way so that we can distort the light in ways that we want. Produce images of objects that are bigger or smaller than the original size. I've got lenses in front of my eyes right now. So does 1, 2, 3, 4 more of you here today have lenses in front of your eyes as well. Some of you have contacts in. Those lenses bend the light or refract the light to change the direction to compensate for the poor job that the natural lens of my eye is doing at refracting the light. I have diverging or concave lenses in front of my eyes. These are lenses that are thinner in the middle than they are at the edges. Now this is pronounced, this is exaggerated, but you get the idea. Okay, my lenses, and I'm sure Alex yours are too, and I'm sure yours are too, and I'm sure yours are too, are thinner in the middle than they are at the edges. Reading glasses are thicker in the middle than they are at the edges. Reading glasses are convex or converging lenses. Now, here's what happens for me, and here's what happens probably for the 4 other people in here that are wearing glasses as well right now. When light comes through the convex or converging lens in my eye, the rays of light converge. They come together. But they're supposed to come together on the retina of my eye at the back. But in my case, and in your case as well, they're coming together just in front of the retina. So that doesn't mean I can't see the image, because the rays of light still go back to the retina, but they're not focused on the retina. Therefore, I see, when I don't have glasses on, a blurry image. It's the blur projected onto my retina. The actual focused image is projected just in front of my retina. So what I have to do is wear concave or diverging lenses to cause rays of light that are coming in to diverge, to spread apart, and then enter the lens of my eye and come together a little bit further back. So because they're coming together too soon by the convex or converging lens, we got to spread them apart so that they come together a little bit further back. Now, if you have reading glasses, and most of you, probably none of you would have reading glasses at this point in your life, okay, before you laugh at the people that do have glasses, know that you will have reading glasses at some point in your life. All of you will need reading glasses at some point in your life. You're going to need, you're going to need, you're going to need, and you're going to need, and you're going to need, and me, we're going to need bifocals. Because at some point, we're going to lose the ability to see things close up. Bifocals, by the way, are just both lenses. You got both at the same time, one on the top and one on the bottom. So here's what happens. Here's what happens when you have when you need reading glasses. The rays of light that are coming through the convex lens in your eye converge, but they converge behind your retina. So they focus behind your retina, not on your retina. That produces a blurry image on your retina. So what you need is another convex lens or another converging lens in front of your eye, like this, in order to cause the rays of light to converge a little bit before they hit your eye lens, so that it's kind of a double whammy for the light, right? It's not converging enough because of my eye lens, so we cause it to converge a little bit by an artificial lens in front of my eye, and then the eye lens can do the rest of the work to cause it to converge on my retina. Does that make sense? How many of you guys, yeah, that's right, eat your carrots, right? Eat your carrots and none of this ever happens to you, right? How many people know who Chris Hadfield is? Everybody knows who Chris Hadfield is, right? Just about? A few years ago, everybody would have known who Chris Hadfield was. Everybody your age. Chris Hadfield is the first Canadian commander of the International Space Station. He was up there for 6 or 8 months, and he was in charge of the International Space Station for that time. And when he was up there, he was the first real astronaut to make space accessible to people. He would tweet photos every day, and he would post videos to YouTube and to Facebook and to whatever, explaining things. This is what I saw today. He'd take a picture of the Earth. Okay, I remember at one point actually, you can look up on the NASA website when the International Space Station is going to go overhead. And I remember doing that one time. Took my son out. He was little at the time. Took my son out south of Okotoks, just south of Walmart, so that we could look up. We see the space station overhead as it goes overhead. And the next day, Chris Hadfield tweets a photo of Calgary and Okotoks. So literally, I mean, not that you could see our car or us in that photo, but it's kind of neat to think we're looking up at the exact same time that he's looking down at us. Well, not at us, but you know what I mean. He tweeted this photo one day, and as soon as he did it, I copied it and saved it because I thought it was perfect, a perfect illustration of what we're talking about here right now. Refraction, and specifically refraction involving lenses. There's a drop of water in front of Chris Hadfield's face right now. Why is that drop of water, first of all, perfectly spherical? It's not teardrop shaped like we normally expect a drop of water to be. Because you don't have gravity, right? The forces of cohesion within the water, of course, are going to cause a uniform shape unless there's some other force that kind of drags it down. So of course it's going to be perfectly spherical in the absence of gravity that kind of drags the bottom of it down. Now you can see that drop is perfectly spherical, or more or less perfectly spherical. It acts as a convex lens, or as a converging lens. That causes rays of light to come together, to converge. And that can produce, depending upon where the object is, and by the object I mean the thing that you're trying to project, the thing that you're trying to view differently, depending upon where that is, it can cause all kinds of different images. In this case, if you look closely, you can see the image of his face is projected through the lens upside down and smaller. You see that? Here's his nose, here's his eyes. His eyes are really close together compared to where they were up in real life. So the image is smaller and it's upside down. Now, do you always get a smaller and upside down image every time you have a convex lens? No. Convex lens is a magnifying glass, right? That produces a right side up image and an image that's bigger. Magnifying glass wouldn't be very good if it made this tiny little print in the newspaper smaller. It makes it bigger. So today what's going to happen is that we're going to learn to draw what we call ray diagrams that will allow us to predict the characteristics or the attributes of the image that we'll see given different scenarios of where we place our object. We place our object here, this is what it's going to look like through the lens. We place it here, this is what it's going to look like through the lens. All right. The demonstration you saw the rays of light that were parallel to that thing that we call the principal axis. This is the principal axis, by the way, that thing that we said goes right through the middle of the lens and is perpendicular to the lens. The rays that were parallel to the principal axis converged at what we call the focal point. This is our focal point. This we're going to call 2F. Doesn't really have a whole lot of significance other than as a little spacer. We'll talk more about that in a minute. This point right here, we're going to call the optical center. Sometimes we abbreviate it as the OC, the optical center. Now, this arrow that's pointing up here on the left-hand side, this is going to represent our object. In the demonstration that we just did, it would represent the Canadian flag that we had on the front board, or the cars that were out on the road that we were looking at through this lens. Okay, the object, it can be whatever, as long as it's whatever it is that you're trying to project. Now, the object, in this case, the object distance, or the distance from the object to the lens, is greater than 2F. You can see these dots over here just representing the spacers of F and 2F, the focal length and twice the focal length. And you can see that the object distance is greater than twice that focal length. We're going to draw two rays of light coming from this object, and we're going to use those two rays to determine what the image is going to look like. Keep in mind as we do this, there's thousands or millions of rays of light coming from this object. We're picking two. The reason we're picking two is because two's enough to tell us what our image looks like. And the two that we're picking, we're selecting those particular ones because they're predictable. And we could pick any one of a number of other million rays, but these are really predictable, so let's pick the easy ones. The first ray that we're going to draw is going to reflect off of the top of this object. Let's say this object is an old guy with a shiny bald head. Light is reflecting off of the top of this shiny bald head. And it's going parallel to the principal axis. Why did I draw parallel to the principal axis? Well, there's rays of light that are going this way, and this way, and this way. But I don't care about those because I only need two to determine what the image looks like, and the two that I'm about to draw are easy and predictable. So this first ray that we're picking is the one that's reflected parallel to the principal axis. Now from there, it will refract or bend by Snell's law down through the focal point. All rays, remember, all rays parallel to the principal axis will refract through the focal point. Now the second one that I pick is going to go from the top of the object, from this bald, shiny head, down through the optical center, and it's going to keep going straight through. By the way, I'm lying a little bit when I draw them like this. The reality is the ray of light, when it strikes the boundary between the air and the glass, it bends. And then when it strikes the boundary between the glass and the air, it bends again. It doesn't just go straight to the middle and then down. But we draw it that way because it's easier and it works. Just doesn't really happen that way, right? It bends twice, when it comes into the glass and then when it comes out of the glass. Now, where's my image formed? This is the bottom of my object and the top of my object. This is the bottom of my image and the top of my image. So my image is formed from the principal axis to where the rays converge or come together. Notice that they're not converging at the focal point because these rays aren't both parallel to the principal axis like they were in the demonstration that we did. We will always identify three attributes or characteristics of an image. The first one will relate to the size. Is it larger? Is it smaller? Or is the image the same size as the object? Look at the red image, the black object. The red image is smaller than the object. So just like in the demonstration, when you saw the projection of the Canadian flag on that piece of paper, the image was smaller. It's not always smaller, but it is in this case. The second characteristic relates to we sometimes call it the attitude. And the attitude says, basically it's right side up or upside down, or upright or inverted. Is this image, this red arrow that's pointing down, right side up or upside down? It's upside down, it's inverted. And the third characteristic, this one's a little bit harder, especially right now. We have to distinguish between a real image and a virtual image. A real image is an image that can be projected onto a screen. When you saw the demonstration, you saw the image of the Canadian flag being projected onto a screen. That was a real image. When you go into the bathroom in the morning and look in the mirror, you have to physically look in the mirror to see your image. You're not projecting that image onto a piece of paper or the wall behind you. That's a virtual image. So when we can project it onto a screen that's real, when we have to look into the lens or mirror to see it, then it's virtual. How do we know? Like, how do we know by looking at this whether we can project it onto a screen or not? Well, here's the rule of thumb. When solid lines, and the opposite of solid lines are dotted lines, and you don't see any dotted lines here. When solid lines intersect, then we have a real image. When solid lines intersect, we could, if we wanted to, project it onto a screen. Doesn't mean we have to, but we could if we wanted to. The image formed by the lens in my eye is a real image because it's formed on the retina of my eye. But you know when I take my glasses off that the image isn't very focused on my retina because the image is formed in front of my retina. There's no screen there to produce a good, sharp, focused image, but we'd still call it a real image because it could be projected onto a screen if there was a screen there to be projected onto. So real can be projected onto a screen, solid lines intersect. Virtual, you got to look into the lens or mirror to see it, and that we know that it's virtual when dotted lines intersect. And you'll see what I mean by that in just a few minutes here. Let's look at the second one that's on the sheet that I gave you earlier. This time our object is right at 2F. Remember, this was F and this was 2F, and on the other side we had those spacers as well. We're going to look at, once again, two rays. The first ray is reflecting off of the shiny bald head, parallel to the principal axis, and it goes down through the focal point. The second ray goes down through the optical center, and where does it go? Straight through. You should find that the image of this object is located right here. This image, where these rays intersect, is larger, smaller, same size. Looks to be same size. I'm not sure exactly why you would want to project an image that is the same size as the object, not magnifying it or making it smaller, but you could if you wanted to. What about the attitude of it? Is it right side up or upside down? It's upside down, or we'll say it's inverted. Is it real or virtual? Solid lines intersect, which means we could project it onto a screen, which means it is a real image. Now, if we wanted to project this onto a screen, we'd have to put a screen right there. If we didn't, that's okay. We could just look into the lens and see the image. But we'd still call it real, not because it necessarily is being projected onto a screen, but because it could be projected onto a screen. What about the next one? This time we're going to say our object distance is greater than F, but it's smaller than 2F. It's in between F and 2F. And we're going to have millions of rays of light reflecting off of this object, but we're going to pick two, the same two as we've been picking so far. First ray, top of the guy's shiny bald head, down through the focal point. Second ray, down from the top of the shiny bald head, through the optical center. And they're going to converge down here somewhere. The image is drawn from the principal axis down to where they intersect. What do we see with this image? Larger, smaller, same size? Larger. Is it right side up or upside down? Upright or inverted? Inverted, yeah. It's flipped over. And is it real or virtual? It's real. We know that it's real because solid lines are intersecting, and the meaning of that is that it could be, if we wanted to, projected onto a screen. Now listen, I just gave you a hint as to where this can be used. Projector. That's exactly it. Look at the projector right now coming out from the wall. That projector is upside down. We have an image that is right side up, flipped over relative to the projector. Make sense? We have an object in that projector that's really, really small, a little small LCD panel, and then it produces an image that is bigger. So bigger, inverted, and projected onto a screen, or real. Okay? Next one. This time, the second to last time for today, we've got an object distance that is equal to the focal length. So if our focal length, if we measured it in the little demonstration that we did to be 12 centimeters, if we put our object or our Canadian flag 12 centimeters in front of the lens, we wouldn't get an image produced. There would be no image produced. Zero. There's no image, period, produced. Let me justify that for you. First ray goes parallel to the principal axis down through the focal point. Second ray goes down through the optical center. Where do these rays converge? Nowhere. If they don't converge, there is no image. So it's kind of wacky. Like, you look at this lens when the object distance is bigger than f and there's an image. Maybe bigger, might be smaller. It's always going to be inverted, but there's always an image. When you look at the object, put the object really, really close to the lens, there'll be an image as well. It'll look different, but there'll be an image. But when you put the object right at the focal point, there won't be an image. Doesn't matter what you do. You can physically look at the lens, right into the lens, and you won't see it. If I took that big Canadian flag, put it 12 centimeters away from the lens, if the focal length was 12 centimeters, and I was on the other side of the lens and looked through the lens, I would not see the flag through the lens. Now, I would see light. I would see redness. I just wouldn't see an image. An image is something that's focused that I can recognize as the object. And I wouldn't see that. Finally, we're going to make our object distance smaller than f. This time we'd say our first ray parallel down through the focal point, second ray down through the optical center. Where do they intersect? They don't. Unless we extend them backwards like this. Now, the extensions of the rays intersect, or the dotted lines intersect. And if the dotted lines intersect back here, we've got an image that is larger. We've got an image that is upright this time. And we've got an image that is virtual. Dotted lines are intersecting. So for this one, although there is an image, you can't project it onto a screen. You physically have to look into the lens to see it. If not the last diagram, but the diagram before that was like a projector, what's this one? What is it? Yeah, it's exactly what it is, a magnifying glass. Okay, let's say that Kathleen is writing really, really small on her paper, and I can't see that because of my old eyes that need reading glasses. So I take a magnifying glass and I put it in front. And all of a sudden, what do I see? Well, as long as my magnifying glass is close enough to the paper, if the focal length is 10 centimeters and my magnifying glass is 6 centimeters away from the paper, then I see an image that is, look at it. What do you see?
Bigger.
Bigger, right side up, and we have to physically look into the lens to see it, so it would be virtual. Larger, upright, and virtual.